So from the proposition that we ended on last time, a pretty immediate consequence is that every k-injective morphism has the right lifting property against all k-relative cell complexes and their retracts. Because in particular we showed that this class was closed under coproducts and forming retracts, and the projectomorphisms are closed under transfinite colimits. I believe we used this result in one of our earlier results, so it's nice to have it now. So being closed under retracts is a pretty cool thing. This lemma says that for any category, its class of isomorphisms is closed under retracts. Well, this is pretty simple. We have our retract diagram, and suppose that F is an isomorphism. We want to show that G is an isomorphism, but we can just reverse the isomorphism to get this. So how far can we run with this idea? We'd like to say something about weak equivalences being closed under forming retracts. This isn't true for all categories with weak equivalences, however, but it is true for model categories. So again, let's start with the retract and assume that the middle morphism W is a weak equivalence. We want to show that F is also a weak equivalence, but okay. First, let's consider the case that F is a fibration. Well, we are in a model category, and so cofibrations, acyclic fibrations are weak factorization systems. So let's factor W as such, i.e. a cofibration followed by an acyclic fibration. But since W is a weak equivalence, which are closed under 2 out of 3, the cofibration through which it factors is in particular a weak equivalence, i.e. an acyclic cofibration. Well, why do we do that? Well, ideally we'd like to get this resulting diagram to commute. We'd have this diagram without the top-middle acyclic cofibration, but we wouldn't necessarily have the middle morphisms. Well, we'd have that the first middle morphism, S, is the top horizontal followed by the middle top morphism, but we would have the second middle morphism, T. The only reason we have it now is because F is a fibration and hence has the right lifting property against acyclic cofibrations. So T is a lift, and that's why we have that this entire diagram commutes. Well, then look at the bottom two rows. This exhibits F as a retract of an acyclic fibration, and we showed last video that these are closed under retracts. So F is an acyclic fibration, hence in particular a weak equivalence, and we are done with the case that F is a fibration. For the general case, we can factor F as an acyclic cofibration followed by a fibration, like so. Now let's do a push-out in the top left. We showed last video that acyclic cofibrations, which are projective morphisms, are closed under pushouts, and hence this middle vertical top map is an acyclic cofibration. Well, remember that we have a map x to y, and so we have a square AXBY that is a pushout diagram. Hence we have a unique map from x prime to y by the universal property of pushouts. This map by 2 out of 3 is a weak equivalence. Our last missing map from x prime to a comes from a lift by virtue of the map from x to x prime being a projective morphism with respect to fibrations. So the square here is x, a prime, x prime, and b. Well, by what we just showed, since this exhibits a fibration as a retract of weak equivalence, this means that the bottom left morphism is an acyclic fibration, and hence the entire left composite morphism is a weak equivalence, and we are done. Our next lemma is sometimes referred to as the retract argument. So if we have a composite morphism and the entire map F has the left lifting property against the second map P, then F is a retract of the first map I. Dually, if F has the right lifting property against the first map I, then F is a retract of the second map P. We will prove number 2 in the other cases dual. So let's write our composition in this way so the liftings become clear. By assumption on F, it has the right lifting property against P, so there is a lift G from Y to A, We can rearrange this and then observe that since I compose P is F, we can complete the diagram in the following way, which does indeed exhibit F as the retract of I as desired. So for the last part of this discussion, we want to talk about what is called the small object argument. So given some category, when can we factor a morphism as a C relative complex followed by a C injective morphism, where C is of course a subclass of morphisms? Well, let's try to. Let's consider all possible ways we can attach C cells to X. A way to think of this all possible ways notion is to consider the set of all commuting squares of this form. So dom and code are just stand-ins for domain and codomain, which aren't specified. Again, all possible squares. Well, okay. We want to factor the right morphism as a C relative complex followed by an injective morphism. Well, let's push out and we get this x1, which is by definition a relative cell complex. Great, and now we can, by the universal property, construct a map from x1 to y. In fact, we can rearrange it like this so that lifting properties become more apparent. Well, have we achieved our goal of factoring F as a relative cell complex followed by an injective morphism? Well, we certainly have the top right morphism as a relative cell complex, but is the bottom right one an injective morphism? So that would mean it lifts morphisms in C. Well, in order for that diagonal map to be a lift, there needs to be a morphism across the middle, making the square, So can't we just define that to be the composite of the top horizontal and top right morphisms? Sure we can, but remember, injective morphisms admit lifts for all possible commuting squares, and our new commuting square we defined with this composite does not cover all such maps from dom C to X that commute. It only covers those maps which factor through X to X1. So we can think of the failure of the bottom right morphism being an injective morphism as being measured by the map X to X1. Well, this is a pretty large error. It's intuitively 50% of the entire map F. So how can we do better? Well, take the map we want to study, x1 to y, and repeat the same process. Well, now x1 to x2 is a relative cell complex, and relative cell complexes compose to relative cell complexes. So a map from x to x1 to x2 is a relative cell complex. We'd still like for this final map x2 to y to be an injective morphism, and its failure to be one is this time measured by the map x1 to x2. Intuitively, this error is now 25% of f, 50% and 50%, which is way better than our previous 50% error. The idea of the small object is making precise how far we can run with this process. Of course, the hope being that we'll eventually achieve 0% error from being an injective morphism and have the factorization of F as a relative cell complex, followed by an injective morphism. So a small object is what will enable us to achieve this intuitive 0% error. Here's a simple version that suffices for our purposes. We say that a category has small domains if there is an ordinal alpha such that for every C in the subclass of morphisms, and every C relative complex given by a transfinite composition, every morphism from domain C to X hat factors through X beta to X hat of order for order beta less than alpha. So back to our previous example, this would give us that since every morphism from domain C to X1, for example, factors through X to X1, we don't lose any generality by defining that middle morphism from domain C to X1 as the composition. So with this requirement, our previous discussion proves that we can factor any morphism as a C relative cell complex, followed by a C injective morphism. What is this locally small category condition? It is saying that we can consider each of its Hom sets as actual sets, so basically that our chosen class of morphisms is small enough for things to work out like we want them to from a set theoretic perspective.